Today we want to talk about naming binary and ternary ionic compounds and binary molecular compounds. We're going to start with the easiest one first. But before we start, we have to have a set of tools. What we need to have is a periodic table. Secondly, we need to have what they call a polyatomic table of all the ions in their charges. Some instructors give them to you, others require you to memorize them. So that'll be dependent on your instructor. The third thing is we need a table that gives us the Greek alphabet from 1 to 10. Again, some instructors require you to memorize it, others will let you have it. The fourth one you need is what they call a table of common atomic anions. But there's a simple way of doing that, and I will use that instead of the table. Okay, so let's begin. First of all, what is a binary compound? Let's try something simple. It's got just 2 atoms in it. All right? A ternary has 3. So that's the first phase. The second phase is, what is a molecular compound? A molecular compound is a nonmetal. Okay, where are nonmetals on the periodic table? I have the periodic table right here, and the nonmetals are all above the line right over here, and they are colored in green. These are the nonmetals, the typical nonmetals. So if you have a periodic table, you may want to do that. Some tables already come equipped with the line that delineates it. Second thing is, once you determine nonmetals, and in this compound both atoms must be nonmetallic. Again, nitrogen is here, sulfur is here, fluoride is here. So you can see they're all nonmetals. So what does that mean? The term I use is you go Greek. It's this simple. You look at the numeric on each one of these, you look for the Greek prefix, and you name it. Okay? In this case, it's 2. That's dinitrogen. And the first term in all of these, whether they're ionic or binary molecular, is this term is always the generic term you would call it in the periodic table. This is pentafluoride. Now in the periodic table it's called fluorine, but for purposes of naming, everything has IDE. If you notice, IDE, 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 IDE. So instead of having that fourth table, just know on the back end it's always IDE. So dinitrogen pentafluoride. This one, sulfur hexafluoride. If you notice, we don't say 1 sulfur hexafluoride, it is sulfur hexafluoride. The 1 is taken as true. You don't have to know about it. Okay, that's binary molecular compounds. Those are very straightforward. The next ones are a little more difficult. They are binary ionics or ternary ionics. First of all, what's an ionic? A metal plus a nonmetal. Okay. Let's try something simple. Everything to the right of this line is a metal. Okay? Now, what kind of metal it is another discussion, so we're going to talk about it. Okay? We have 3 categories. Binary ionic, in which it's a group 1 or group 2, or aluminum, zinc, and silver. Okay, where does that mean? All the blue is group 1, group 2, and aluminum, zinc, silver. When you see that, you know it's what they call a binary ionic without transition metal. How do you name it? Same thing, name of the cation, name of the anion with IDE. The cation here is sodium, again, just like the way you say it. But unlike the molecular, you don't care if there's 20 over here. It's still going to be called sodium oxide. This one, because it's one of those special elements in the transition area, when I say the transition area, the rest of the table is transition elements. And in a second I'll get to you and tell you what a transition element is. Same thing here, aluminum oxide. Just the way it sounds. You don't say aluminum oxygen, you say oxide. Okay, so that is what they call binary ionic non-transition. Now we have to go to transition metals. What makes the transition metals different in the naming is their inherent ability to have what they call a multivalent. So how do you tell the difference in a transition element if it has more than one valence? That's why you go to what they call the Roman numerical. What that means is a +2 is a Roman numerical 2, +3 is 3, and that's a 3. And we have situations where we have a 4. And a 4, again, is the Roman numerical 4. Right now, those are probably the only ones you're going to worry about. So now, again, we look at this. Iron oxide. We know it's iron oxide because this is a metal, this is a non-metal. But this is a transition metal. So what do? Well, we got to figure out the charge. To figure out the charge, there's an easy method. It's called the crisscross. It's a fancy way of saying you look at the subscript on this side if it's not 1, and that's going to be the charge on this side. So this is, if you look here, it's 3, and we're talking binaries right now. So that means iron 3 oxide. In this case, we're not worried about the anion because it's always going to be IDE. So now let's look at this. COF3. Same thing, we cross it, and that means this charge is going to be +3. So this is going to be called cobalt 3 fluoride. And that's how you handle transition elements. Now let's talk about the next one, ternary ionic. Ternary ionic is a fancy word for a polyatomic ion as one of the components, meaning a polyatomic ion, even if it's 2, for purposes of charge is considered as 1. So, for example, 1, 2, 3. Okay, the polyatomic is this. Now, how do you know this is a polyatomic? Your instructor will ask you to probably memorize that sheet that you get. Okay, so, but you treat polyatomic ions as a non-metal, except, there's always an exception, ammonium, this is ammonium, is treated as a metal, so when we're doing this, we know it's a metal plus a non-metal. Okay, so let's go into some of the labeling. Something I have here that you will not see in the book. I have a bracket over anything that does not have a number greater than 1. Purpose of this bracket is so that you can see the polyatomic. Technically, this is what I mean is 1. So each one of these is a 1. Okay? That's for you to try to say, oh, it is a polyatomic. I need to go to my polyatomic cheat sheet and find out how to name it. Once you know it's a polyatomic, the naming convention is identical to the convention for a binary or convention for a transition, depending what the positive ion is. Now, the positive ion is always on the left side, the negative ion is always on the right side. So this is sodium carbonate. This is calcium nitrate. Again, it's memory for this part. The rhyme or reason, whether it's ATE, ITE, etc., there's no consistency. You can't find a way to easily do it. The next one is iron. Okay. Okay. Oh, we got a little problem here. 1 to 1. What do we call it? This is where we go and backdoor it. When I say backdoor it, we know what the charge of this is because we get that from the table. So we know this charge is -2 from the table. So since there is no charge total on this, this has to be +2 to make it equal to 0. So that's why it's called iron 2 carbonate. Same thing for here. When you go on the table, you'll see that phosphate is a -3. Iron then therefore has to be a +3. Okay, now let's go to this one. This is ammonium. How do we know what the charge on chloride is going to be? We know from the table ammonium is 1. So this is going to be ammonium chloride. Because it's a polyatomic, all we have to do is name it. This one, same thing, ammonium phosphate. Because it is not a transition element, we do not have to be worried about a Roman numerical. That's it for this section.